Good evening. How are we doing tonight? Shouldn't go too long. I'm going to have to, of course, clean up some stuff in editing, post, production, editing. I don't want this to be too long and boring, but I just think it's important that we examine what we're looking at and why it's important not to speak rhetoric 8 inches per mile square. I just heard it on another channel from a large YouTube, the godfather of FE. Talk about 8 inches per mile square to one of his interviewers, someone that was interviewing him, or he was interviewing a grad student, I don't know, something like that. And you can't mention 8 inches per mile square because it absolutely doesn't divulge anything about anything. It's not even a good subroutine or a good pre-calculation. And can we see what we're looking at? That's basically what I want to get out there. And for you to use your own brain, your own mathematics, and there are some things that you should know. Can you see something? Right? We're always talking about you're here and something's over here. And we're saying, can you actually see from A to B? Can you see it? Well, you have to take into account how tall is this person? Or are they on a mountain or are they on a bridge? And how tall is this? I mean, just looking at this graph, here's the eyeballs, looking onto that, yeah, you can see it. How much is visible? Well, we got to talk about a couple things. Can you see from here to there? Actually, let's go from here. Let's use a straight line. Here to there. Ooh. Looks like you can't see the bottom, right? If you look straight to the bottom, well, let's look at another line. Let's look at this line, a tangent. Tangent means touching the circle at one point. So it looks like there is some portion here that's invisible and some portion here that's visible. That's all we want to cover. And how to figure out what's the math behind it. And it's definitely not 8 inches per mile square what you can and cannot see, because we have to examine something. And let's bring up this program that I made. I believe I alluded to it. I made this program a couple of years ago and never got around to sharing it because, well, I just don't think people really care about the subject. And this thing that we're in right now, should we even care about this right now? It's not like it's going into the history books, right? So can we see something? Let's just do, because if we talk about actual distances, 10 miles, like across the lake or something, that's the graph. This is to scale. That is the graph. And that's 10 miles away, that wedge right there. And if we zoom out so we can draw some pictures, well, you can't really draw a diagram on a graph that small. So like we discussed before, we have to exaggerate. So here, just for reference, I'm using radius 3959.934139, and I believe everything that I did here for display purposes is round off. So I used a constant circumference of 24,881 miles and a derived radius. So let's talk about this wedge. Talk about the distance of 3,000 miles. Can you see from A to B? And let's put in some dots. So those are the dots, A to B. Let's use, so I can zoom in. So there's 1,000 miles, A to B. Can you see it? Well, what's 1,000 miles? 8 inches per mile squared. That again. Now, this is to scale. So let's put in, now this is feet. Spike A is going to be the height of whatever's standing at A. So let's make it 1 mile high. So you can see it. See, that's a mile high. And because this is to scale, that's a mile right there. But now we're missing the other 10 miles, or 1,000 miles. We can't see it. Well, if this was 10 miles, it should be 1/10 the distance. Now you can pause it, break out your ruler, whatever you want to do. But that distance, that spike right here, and I know it's faint because it's a thin line, and I did that on purpose because I didn't want it to overshadow the speaking points here. So if you get out your ruler and hold it up to the screen, this is 10 of these spikes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is going to go from A to B. Let's make spike A also 1 mile long, or spike B. They're both 1 mile. So we can look at it on the graph. Because let's zoom back out. That's not a graph you can really talk about on a diagram because it's literally flat. Not literally, but visibly it looks flat to the naked eye. Right? Just like every straight line looks straight to the naked eye, but by definition of a straight line, you can neither draw a straight line nor measure a straight line. It's literally impossible. Now we can get close. Anyway, that's another topic altogether. That's all theory stuff. But so we can draw a graph. Let's do 1,000 miles. And go ahead, break out your calculator or your pencil and paper and let's do. Can you see? Well, see, look. You can't even see those red lines. So let's make this, if you had a 0, a 1 mile, and you had a 0, now they are 10 miles. Let's calculate that. I'm sorry. Yeah, 10 miles high. So now that we added some height, that's a 10 mile high spike. See that? But even at 10 miles height from A to B, we're going to have to do super exaggeration so we can look at this graph. Let's go 100 miles. All right, now we can see from A to B, A is 1,000 miles tall. I'm sorry, 100 miles tall. And B is 100 miles tall. At a distant, an arc length of 1,000 miles away. Is it visible? Well, it's always important to draw a graph. Can A see B? And can A, from A's vantage point, see all of B, all of it? Well, this is drawn to scale, but what if you didn't write a program that drew something to scale? You would have to 100% rely on your math, and that's what we're going to get down to. Analogy, your mathematical concepts, your mathematical skills, applying the principles of math to something observable. And we're talking about a circle. We're not going to get into the name game circle versus sphere, okay? We're looking at a two-dimensional diagram. So for all intents and purposes, we're talking about a circle, although we're talking about real-world problems, it's a sphere, but we're looking at a circle from a distance. And when you see something at a distance, we're going to ignore the depth. We're just looking at two axes, X and Y. And just so you can see the grid, I just added this recently, although I created this program. Oh, those are the angles. I did this recently so we can have a little more perspective. So each square, I believe, is 100 miles wide. So I drew a grid so you can see here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 1,000 miles. If I zoom in just a little bit, see how it's not quite touching because of this curve? So, can A, C, B? It helps when you draw a grid, right? So if you were using some paper, what do they call that paper? What do they call that paper? Grid paper? I don't remember the name of it, but I use now on top here because I went from the origin, which is 0, and I went up. So it's not going to be a complete square on top. But it's a good visual aid. You can see from here to here. That is a 10 miles, right? 100 miles tall and 100 miles tall. For sake of argument. Well, let's draw some lines. What about, so that's the angle we're looking at from A to B. And what's that angle? Let's look at the angle. So typically when I'm discussing the arc length from A to B, in this case 1,000 miles, typically I'm going to call that angle from A to B in this wedge right here theta. Go ahead. What's 8 inches per mile square? Doesn't really matter. Let's get rid of this grid here. Can A, C, B? And I forgot, I haven't looked at this thing in a long time. I forgot where I put the, here we go, rotate. This is what we're really asking. Can A, C, B? Now, people are always talking about the drop, 8 inches per mile square. And that is so wrong on so many levels. And this is why. That's the drop right there. That is the drop. Okay? Let's put something else up here. Let's look. The bisect divides the total distance on the surface in 2. Let's bring up one more thing. A looking onto B, can you see it? Now, you're looking straight at the person. Let's call person A and person B, okay? That's a secant line. So now that I have the secant line, or the chord, because we're talking about a line inside of a circle, a straight line inside of a circle from edge to edge. So we can also call that chord, drop that arc off. So now, does the drop have anything to do with what you can see? Look at that. Here's the drop from A to this pink triangle on the inside. And can you see B? Now let's rotate it again. Can A see B? There's the drop right here, this space. Does it have anything to do with what you can see? This guy A can see guy B. Now what does the drop have to do with it? Has absolutely nothing. Now this is using observation. I hope that's absolutely positively clear. And I'm spending a ridiculous amount of time just trying to point out this very fact. And let those people know, stop talking about 8 inches per mile square. Yeah, it's an estimate for close distances, but it has nothing to do with what you can see. See that? I mean, talking about beating a dead horse. And here is the, I'll get rid of that bisect line. And we're going to add the, what I call the bump height line. And I guess it's also named after a star constellation. They call it the Sagitta. So hey, why not? Well, whatever. It's just nomenclature. There's the bisect line, but Sagitta. That's the height between the two things. There's the drop. There's the height. But looking at this diagram, oh, clearly A can see B. Clearly. Well, let's see how much of it. Now, here's the apex. No, I don't want to draw the triangle. I want to draw the apex dot. There's the apex dot. Right there in the middle. That is the apex of the hump. The bump, okay? Now, let's draw line of sight. I'm going to call from A, the top of A, looking at the top of B. Okay? I call that line of sight. So line of sight, if you were to look from A onto B, even if there was a hump in the way, that's the line, top to top. Even if B was a lot taller. Top to top. Or if B was a lot lower. Top to top. See? Now clearly, based on the diagram, and the fact that this diagram is to scale. Now, you could not draw something to scale without really doing a lot of work. So I put the work already in this program. It took me quite a while to make this program. This was a couple years ago, so I'm out of practice. Now, let's talk about, now this apex is a tangent. It's tangent to the middle. But what about A looking on the B? What is A's maximum visibility onto B? Well, we got to talk about, we have to draw a line. There's a tangent line. What is the tangent from the top of A to the circle? So what I'm looking for is, now you can be good at drawing diagrams. Well, see, right now I'm doing this freehand, even I'm using a straight edge. So let's say that's touching at one point. Now, without using any measurements, you can see right there, some portion of B you can't see. But looking at this diagram, you would say, oh yeah, A can see B. Well, how much of B can A see looking onto B? We just drew a line, but still, we'd have to use math. So what I demonstrated right just with that line is, A is now this A looking onto B, and I drew a tangent from A to B. So tangent would be, if the center's here, the tangent would mean that this line, wherever this point, this intersection from A looking onto B, is going to be perpendicular. And by stating that, that means that this angle is exactly 90 degrees. A looking onto B. That is the line that we're interested in. A tangent line from A looking onto B, tangent to the circle. The tangent dot is over here. Notice that this tangent dot is to the left of B, which means there is going to be some height, some distance that's not visible on the tangent line. So, 1,000 miles apart, surface. Now the secant line, or the chord, is the distance between A and B, going through dirt and going through space, going through solid objects. The secant line is the real distance, this blue line, this chord. The walking distance is this arc length. So we have to walk, traverse. So obviously, 1,000 miles is longer than the chord length. See that? We're talking about this straight line, this red line. Now see, we can't even really tell, well, how much a bee is hidden. See that? Even though this is drawn to scale, it's still difficult to make out. I think I'm going to cut this video here shortly, and I'm going to have to make another video because I'm not going to go into the math behind this just yet because I think the video will be way too long. So I'm just going to cut it off here in a couple minutes, and we're just talking about diagrams. We're talking about getting things to scale. And I think this is an important topic, an important concept. So even though I drew this to scale, it's very difficult. So we have to rely on our math. How much is hidden? And we're going to go into that in the next video. Hopefully I'll get around to it. You know, I'm telling you, it's really difficult to come back to this subject because the magnitude of people that ignore these concepts and the magnitude of people that's even far, far larger, people that really don't give a crap, makes it difficult to even speak on the subject. I mean, people find a calculator online and they just point to the calculator and then they talk about facts or something that they're observing and they really don't grasp what they're looking at or how they explain things. And it's very frustrating. I got some data here. Visible. So each, I call them spikes, but each object here, person A is 100 miles high and tall, and person B is 100 miles tall. And this red line here is tangent to the circle. Tangent to the circle. Looking from A on to B is tangent to the circle. So it looks like it's going to the foot of person B, but that's just an illusion because of the scale of the diagram. So if we were to change the tangent of the circle is to the right of B, which means all of B is visible, and the intersection of this tangent line is way above. See the secant or chord down here? Very, very low. Sagitta here, very low. And I did calculate the intercepts. You have to. That's the only way you can get the data here. You can tell on the diagram clearly A looking onto B, the whole thing is visible. All of B is visible. Height visible. There's the height 100 miles, visible 100 miles, hidden 0 feet. And we're going to get into that in the next video, how to calculate those steps. Let's go back to 1,000 miles. Back to 1,500. Let's look at 1,500. Whoa. Looks like about half. Let's see, here's the apex. The apex is in the middle. See there? But the tangent location is to the right of the apex, which means you can see over the bulge, but the angle of attack, I guess, from A looking onto B, goes over the hump because the height is higher than the sagitta. And it goes over the hump, and on the down slope, it intersects right here. And I do have those numbers. There we are. That is the intersect, the tangent. A to circle the points 873 miles away at from the origin going 3862.39 miles up. So the x and y coordinate is here on the tangent. And did I program this into there? Yeah, the apex. So that's 745 miles. And we're looking at what, 1,500 miles? Yeah. Now the apex, we're talking about x. So it's half the chord, not half of the arc length, because we're talking about xy coordinates on the Cartesian plane. If we were to tilt this back, rotate it back, going to the right some x, and going up some y from the origin, which is the middle. The tangent, which is that y dot here, is going over some x, 873 miles and up, some 3862 gets you this coordinate. See how that works? Inner triangle. Pardon me. That's what we want to talk about. 58 miles. 48. See, it's almost 50-50. And if you look at half of it's visible, half of it's hidden. And if you look at this diagram, you can see here. You can just gauge, and it looks, oh, half of it visible. But see, you have to rely on math. You can't just draw a diagram. You can't draw freehand to scale. You can come close within maybe a millimeter, but what's a millimeter to scale? No, you have to rely on your mathematics. And that's the whole topic of discussion. You have to know what's going on. Please, if you have any questions, how to mathematically, what is the math behind this? How do you find the apex? How do you find the tangent location? And I have the math. I have all the math. Where is it? Oh yeah, I did make this. Let's bring that up for a second, so that way you can see what's to come. Here we go. I did this also a couple years ago. As I was doing things on paper, all my scrap work and scrap paper, making sure that all my math was correct, I did come back at some point later on and put it into an Excel spreadsheet to keep track of my ideas. I put some notes here on the side. What we're looking at, the tangent lines here. This is the tangent line A looking onto B. And a tangent line, you got the line of sight from A to B, this blue line up here. The tangent line to the circle, touching the circle at one point and going and cutting here. This length of B, this height of B. And this is the viewpoint looking, skimming across what you can see, a direct line of sight and skimming the highest point visibly. So here's the apex here to the right, but to the left of it is the highest point because the angle of attack goes this way. So that's the tangent line. And the math behind that is here. This length of A, which is height. This length of B, which is inside the circle. And finding some length. And that's the key. Finding the length of this tangent line. And I go into that, how to find it, get all the angles. and it's a lot of work. And an intermediate step, finding the drop, that doesn't say anything about anything. So here's the drop, this orange circle, this orange triangle here. Here's the Sagitta. But still, even knowing the drop in a Sagitta height, it still doesn't tell you what you can and cannot see. It's a very minute intermediate step, a necessary step, but still, the drop doesn't tell you anything about what you can and can't see. Just look at this diagram. Pause it, look over what you're looking at. Pause the video and look at this diagram. I think I put it here, we go, our diagram tab. Go ahead, look at the diagram. There are a lot of steps. There's a few steps. There are a few steps, and I kept track of some things here on the left here. Talking about angles, and we'll get into that. But please post a question, and I'll be happy to, anyone that's actually interested. All right, I think I'm going to sign out for now. Thanks for watching. Take care.